Hello, here's a video related to Project 2 in Math 208, 209. For this project, there are 4 things that you need to do that correspond to the 4 tabs down here at the bottom. The first one, we want a time series plot. The data is related to the trend in train accidents over the past 27 years. As you're looking through this data, consider the most recent train accident over in East Palestine, Ohio, where several cars derailed. No deaths, but unless you're going to talk about the deaths of all the animals, lots of fish and deer and so on have died because the chemicals leaked into or the hazardous materials leaked into the water, a river there. Natural question is, how many accidents are there? How many train accidents are there in, say, an average year? And you're going to investigate that by looking at the data from 1996 to 2022. In the second piece, you're going to look at linear regression. This is similar to the linear regression that we did on the calculator, related to chapter 4 in the course. And we're going to look at crime statistics for this, murder rates and robbery rates and populations of different states. In each case, we'll look at a scatter plot, a line of best fit, and calculate the correlation coefficient. The third problem is on empirical probabilities. This one is most like the one, say, in class, where you have a two-way table, one variable on one side of the table, another variable at the top, and you look at how those two variables are related by looking at frequency data and then linking relative frequencies to probabilities. And as you can see, that we return to the train accidents data. There are over 83,000 train accidents over that 27-year period. And in that one, you're going to look at some of the causes of the train accidents as well as the most popular railroad companies in the country and how those two are related. And then finally, you're going to have a problem from section 6.1 on creating a lottery ticket, an instant lottery ticket. This one is related to chapter 6, section 6.1 of your textbook on expected value. So we have a time series plot from chapter 2, linear regression from chapter 4, empirical probabilities from chapter 5, and expected value problem from section 6. If you turn in the Excel worksheet, this worksheet with all your work on it, and a single PDF document with all the graphs, answers, explanations from the 4 tabs down here. This last tab here, Connecticut, is related to the lottery ticket. There's another lottery ticket here that you have to compare to the one that you create in the lottery tab. And this is due Monday, March 20th. So let's get right into it. In this first part, you're asked to construct a time series graph. And here is a listing of every year since 1996 all the way up to 2022. And here are the number of accidents. So some of these accidents may have been minor. Some of these may have been led to, deaths of individuals. But they're all kind of combined together in this graph. So to construct this graph, just highlight the data, not the total row down there or the header row, but all of the data. And then we're going to insert a graph, and there it is. And this is a first draft, and what you'll want to do is to make it look a little nicer. This clearly is the trend of this data over here. Down here, we have these numbers that look like integers numbered from 1 to 27, as if they were using these numbers over here. And up here, these are the number of accidents. This here is a constant at 2000. Not sure what this is, but we're just going to delete it out. And maybe we'll delete that one out as well. So this is the trend that we want to add a little bit more detail to. So I'm going to make sure that the number down here on the horizontal axis is year. And then we're going to plot these here are the frequencies, which means the number of accidents over the years from this first year, 1996, all the way to the 27th year, which is 2022. Anywhere in the graph, let's go ahead and hit Control-click or right-click if you have a PC. And what we want to do is to select the data. we only have one of these series on here. If you have two, you can just select one and then hit the minus sign to delete it. But we're going to change this one to, we'll just call it train accidents over time. Something like that. That just gives a name of this particular series. When I tab away from it, you can see it changed the name. The Y values are the frequencies. So I want to make sure that it's selected the frequencies. You can see when I highlight this here, the frequencies are selected, so that's good. The next thing is to come down to the horizontal category axis. These are the years over here. So when I select there, nothing is selected. And so I'm going to click on this little rectangle over here, and it allows me to go and select all of these years. When I have the right years selected for the horizontal scale, I'm going to hit enter, and those numbers come down here. Now that's pretty much all you have to do, is to establish the horizontal, the x-axis, establish the y values, give it a name, and you're good to go. You're going to repeat this step over and over again in this project. All right, as you can see down here now, this this horizontal scale markings, these are now the years. It's hard to see, which year. The text itself, 2017 or so on, is pretty wide. So what you might want to do is to spruce it up a little bit. So here's some things you can do. I'm going to highlight this axis and then go home and then change the font size here to 16 just to make it a little bigger. You can make it as big as you like. I'm going to change these numbers down here, which are the years, also to the 16 font, trying to keep it uniform. And then up here, I'll just change this to a much bigger font and then say something like train accidents over time, and then be more specific and parenthetically give the years we're talking about. All right, so we have the train accidents over time. Over here, we have the number of accidents, and down here, this doesn't look very good. So I'm going to select this, and then again, I'm going to right click or control click if you have a Mac, and we're going to format that axis. Over here, you'll see all of the ways that you can format the axis. The one I'm interested in here is, I believe, this one here, and we can send the text direction of that axis down there. Instead of horizontal, we can do it vertical. And I think I like this configuration best. And then notice it puts the years in a vertical format. All right, so that looks pretty good. It's pretty clear what these are down here. This is probably one case where you don't really need a horizontal axis marking, but we'll put one in there anyway. This one here, this would represent the number of accidents. So I'm going to come up here to chart design, and then to the far right is to enter a chart element. For axes titles, I'm going to select vertical, and then triple click on this in here, and then write in the number of accidents. And that's a little too small to read for my taste, and so I'm going to change this also back up to something a little larger, maybe 14. So for the horizontal axis, same idea, chart design, add a chart element, but this time I'm going to do the horizontal axis. And, putting something that's clearly obvious to the reader, which is that this is the year. Oops. And then enlarge that a little bit to a bigger font, maybe 18. And this thing you can move, this legend or this title here, you can move wherever you'd like. And if you want to spruce this up a little bit more, you can add labels. So what I'd like to do here is to control click, and I'm going to select a new plot type, change top plot type. And instead of a line graph, I'm going to do the line graph that puts in the points. So you can see it puts in the points, and you can see where 196 is there. Now, if you click over that, you can actually see the characteristics of the point, 1996, and the frequency 3188. You can play around with adding. If you click on one of these points, it selects them all. If you do another right click, you can format the data labels. And what that does is it puts the data label right on the screen. If you don't think that's large enough, you can enlarge it to say 14. So if you have these highlighted, you can then right click and then format the data labels. And for this, you might want to change the position of the label. Maybe it's center, maybe it's above, maybe it's below. So just choose one that you like the format itself. It's probably going to be the case that not everything is going to look great. So you might want to just select one of these and move it. And notice that if I move it far enough away, because this box is clicked here, the leader line will appear. And those are particularly helpful if you have some labels that are kind of clumped together like these. All right, so you can add some more bells and whistles, and this is your time series plot. And notice that something happened maybe in 2007, 2008, maybe 2008, because from 2008 on, we've had a pretty consistent, constant almost number of accidents. It might be drifting down a little bit in here, but it's somewhere between the 2000 and the 3000 range. And before that, we had up to 4,500 different accidents every year. So maybe the government passed something and, right about here that brought them down. But you could investigate what it is that the government did, maybe some oversight or something like that led to the dramatic reduction from about 4,500 to about 2,000, almost halved the number of accidents in that period. So always start this graph at 0 so that you don't have a misleading graph. You can, in fact, change this. If you wanted to make it misleading, you could format the axis. It looks like the smallest value might be this 2310. So we could actually go from, say, 2300 up to the, say, 4510, way up there at the top. And then if you do that, then you see this new scale where it looks like a much higher increase than it actually was over the years 1996 to 2005. But then you can see this dramatic decrease after that. Okay, let's go to linear regression. In this one, this is a data set that was pulled from this larger data set up here. And I've highlighted the columns that we've used. The government collects these state summaries of all of the crime stats and keeps them up on a crime website. And this data is from 2019, before the pandemic. So what we're after here is for you to construct 3 different scatter plots, one between population and murder rate, one between population and robbery, and the third one between murder rate and robbery rate. And we're going to draw a line of best fit, a scatter plot, and calculate the correlation coefficient in each case, and then describe the relationship between the variables, if there is one. Perhaps there is not one. And then finally, we're going to identify one of those graphs and then identify an outlier. I've copied these 3 columns and brought them down here, and these are really the only 3 that you need. The murder rate in column B, the robbery rate in column C, and the population of the state in column D. A we'll use as the labels. So I'm just going to do one of these. Let's take or maybe I'll do a couple of them. We'll see. And what you want to do is, let's say we're going to look at the relationship between the murder rate of each state and its corresponding robbery rate. So we're not going to select the titles. All we're going to select is the raw data. Now we have data from the 50 states. So just go all the way down. Here they're sorted. The states are sorted alphabetically. And so we want one of those. We want this to be the X and this to be the Y in this particular one. So we highlight the data, come up and insert a scatter plot. And that's this one right here. And so, yeah, it looks like there might be a relationship there. We have an upward trend, kind of a wide trend channel here. But these points tend to, as the X gets larger, it looks like the Y is getting larger as well. This one here is the Y. This is the robbery rate. And what 120 means is 120 robberies per 100,000 in the population. Down here we have the murder rate. There's not as many murders as there are robberies. Therefore, the rates will be a little smaller. You can focus in on individual points. Like this one over here has the highest murder rate because it's furthest to the right. and it has a lower than maybe expected robbery rate. So it'd be interesting to focus in on that city right there, that state right there. So this is the point 11.7 and 86.6. So 11.7. So maybe we can come down here and screw out. Oh, it looks like Louisiana is the culprit there. So later on, we're going to put labels on these. But right now, just to take a look at them. So there's lots that you need to do with this graph. Make sure that for this one here, I don't like that extra 0. So I'm going to come over and format the vertical axis. Yeah, so here's the the format, and we want it to be a number, and then it'll ask us the number of decimal places, and we want 0 here, and then it'll just give us the rates here. Same thing down here. I get rid of that 0. The other thing that you should add on this one here is the trend line. So this is a chart object. And so let's come over and let's add a chart element. And in this case, we want to come down and add the trend line. We're interested in the linear trend line. And so there you see it is. That's where the trend line is, the line of best fit. Notice it starts at the first data value, ends at the last data value. If you click on this trend line and then right click, you can format it. And you want to do this because you want to come down here and enter the equation of the best line fit on the graph, or at least close to it. And you want to display R squared. And R squared is what we call the variance, and it's 0.354. So if you wanted to figure out what the R correlation coefficient is from this, let's go just down to the bottom and just type in R equals, and you can manually get your calculator out and just take the square root of 0.3454. Just type that on your calculator. And when I do that, I get 0.5877. So let's just call it 0.588. So it's kind of the middle of the road. Remember, the highest correlation coefficient is 1 and the lowest is 0, and this one is kind of closer to 0.6. So there is a moderately strong relationship between a state's murder rate and its robbery rate. So there seems to be a connection there. And because there is a linear connection, we can go ahead and make some predictions. So what would you predict the robbery rate for a state that has a murder rate of 8? Well, you go up to the line, and then the line would predict about 8590. Now, here's what I would do to make your life easier. Now, I would actually get as much of the first graph done as possible. And then when you're done, you can just go ahead and copy this with a Control-C or however you copy it on your machine, and then come down here somewhere and paste it. And so that's a copy of the first graph. There's the first one, there's the second one. And now, remember, you're going to create 3 of these. So I'm just going to go in here and change the data or select the data. So let's say that we want to, the series, and we want to compare murder rate by population. So murder rate by population. And the X values, remember this is a scatter plot now, our X values we want to be right here on the B's. It's got both of these selected. So I'm going to go in here and click on this one, and then I'm going to go select the X's. Okay. There. And then hit return or enter. Then I'm going to select this box here, and then I'm going to select the Y's. Now the Y's I want here are the population numbers. So I'm going to select the populations of all the states, hit enter. All right, so we've changed the X and we've changed the Y and we've changed the title. So let's take a look. This one's quite different, but it did put the new line of best fit in there. So I'm going to do a control click or a right click and then format the trend line again. And once again, add the equation and the R on there. And you can see in this one, the R is very close to 0. So there's almost no relationship up here between these two variables, murder rate, population of the state. All right, let me do one other thing here with this one. I'm going to right click on a point, and then I'm going to add the data labels. Well, those are not the data labels that I wanted. I wanted to label each one of these points with the name of the state. So I'm going to click on one of these numbers, and notice it selects all of them. And then I'm going to right click or control click, and I want to format those data labels. What it put right here as the label was the Y value. I don't want the Y value, so I'm going to leave it there for a second. But what I want are the values from cells, and I want to go grab those state values from the column A. So let's come over here and let's select all the names of the states by highlighting them. And there they all are. And I'm going to hit return. And now you'll notice that it puts the state name. And because I don't want the population number there, I'm going to deselect the population. And now I have just the states. So you may want to do it this way, or notice how they're all clumped together. There are 50 of them. Some of them are clear, like this is Louisiana and this is Mississippi, but they kind of get all crowded together. So what you might want to do is just to create some space. You don't have to have them all. You might want to just label a couple of them. You might want to label Michigan, for example. There's North Carolina. Move this one over. And there's Georgia. Michigan's there. I'm gonna put Michigan there, and Georgia right there. And you can spend as much or as little time on this as you want, but at least that way you can go and identify the individual states that are the largest in some way or the smallest in some way and say something about it. Like I would think for this problem, saying something about these states over here in the South that have smaller populations, but very, very high crime rates. You might want to say something about those. And there's one more. And again, you might want to copy this one. I don't think much will come of it, but if we come down here and paste that one, then we can come in here again and right click or control click to select the data. And for this one, we want our X's to be the robbery rates and the Y's to be the population. So we already got the Y's to be the population in this graph. So let's just change the X's. So hit enter. And I think everything else is set. So we say okay. And it leaves them in there. So this one you can see what's interesting is that there's absolutely no relationship between murder rate and the population of the state. The correlation is very close to about 0.06 there. And this one here, this one goes back up. It's not as high as 0.588 like the first one, but it's still fairly large. Again, you might want to enlarge this one a little bit. It shows up a little bit more. There it is. And if you take the square root of 0.2658, you get 5155. So about R equals about 0.516. Again, a fairly high correlation coefficient. So there does appear to be a relationship between the robbery rate of a state and its population. All right, so in terms of outliers, then what you do is you just kind of go through these and say, is there an outlier in this graph? Well, I don't know, maybe. Is there an outlier in this graph? It's hard to say that there's an outlier in a graph where the correlation is 0 because there's not even a linear trend to say that there's an outlier related to it. And this one here, here's the line of best fit. So this point is a ways away. And here you have a couple of candidates up here for outliers as well. So pick one of the graphs and identify what you think is an outlier and describe why it is an outlier. Okay, let's move to the next chart. This one you're going to see is most like the ones that we do in the textbook. So basically you're going to be doing conditional probabilities from an empirical setting, and we're going to use the trained data again. Going across the top, these are the 4 biggest railroad companies in the country, but there are a lot of them. And so a lot of them are grouped in the other category. And then all of these are accidents. And here are 83,000 accidents over that 27-year period from 1996 to 2022. And these here are the type of accidents. So was it a mechanical or electrical failure? For example, did the brakes fail like they did on that East Palestine train? They kind of group all the miscellaneous causes not identified in these other 4. Something related to the track or the roadbed or structures caused the accident. Sometimes it's signaling. Train takes the signal, goes on the wrong track, and then there's an accident. And then there are human errors involved as well. The randomly selected accident was selected at random. What's the probability that the accident involves CSX? All right, so I'll put that right up here. I'll start off by just saying equals. You could just write fractions and do these later if you'd like, but I'm going to do the calculation right in Excel. The accident involves CSX. So here are all the CSX accidents. There are 10,500. I'm going to click on that cell, and then we're going to divide by the total 83,725. So there it is. Now that was the formula D9 divided by G9. So I'm just going to copy that and then paste it in here. So I get the same thing, but then I can turn that one into a percentage, give it a little bit more precision so you can see it. Makes it a little bit easier to read. And the next one says the accident was caused by a signal or communication malfunction. All right, so I'm going to assume that that means signal and communication. So again, I'll use the equal sign. I'll take the 1852 and divide by the total of 83,000, and you can see that's pretty small. In the next one, the accident involves CSX and was created by a signal. So that's both CSX and signal. So there's that many there. So I'll type in equals and then go grab CSX and signal and communication, and then divide by, again, the total. But we can convert those into percentages as well. The next one is the accident involves CSX given that the accident was caused by a signal or communication malfunction. So this next one is a conditional probability, because you can see here that it says given that the accident was caused by a signal or communication malfunction. So that's the denominator. So we look at the total of the signal and communication malfunctions, and that's right here. So of these 1852, how many of them were CSX responsible? So for this one, we take equals the CSX and signal and communication, and we divide by the total number of signal and communication accidents, 21%. This is the same two events, but they're in reversed order. So the accident was caused by signal and communication, given that the accident involved CSX. So now we're talking about these 10,500 accidents caused by CSX, but we still only have 389 that were caused by signal and communications. So for this one, we take the 389 and we divide by the 1050. Very, very small. And the last one is an OR probability. So it's CSX OR. So for this one, we're going to take all of the CSX plus all of the signal and communications. But in adding those two row and column totals, we've added the 389 twice. So I'm going to subtract it out once and then put parentheses around that sum to follow the order of operations. And then at the end, we're going to divide by the total. And there's the total. Once you get these decimals, if you want to make them pretty, you can just highlight the whole thing and then convert to a percent. If you want more precision, you can add more decimal places there. And here's another way to do those same probabilities. When you look at, are the events E and F independent? All right, so to check for independence, what we have to do is to identify our two events. And so the probability of E, that would be the probability of CSX. That was this 0.254 number. So I'm going to bring that one over. There it is. Probability of F would be the accident was caused by communication failure. So I'm going to just, I've already calculated that. There it is. And the probability of E is also here. The probability of F is also here. And for this one here, I'd have to take the probability of E, this one, and then multiply it by the probability of F, which is this one. And then the probability of E and F is this one here, involved in accident and was caused by a signal, that one there. So for this one, I'm just going to type in equal that number right there. And the probability of E given F, if we say that E was CSX and F was caused by signal or communications malfunction, we're looking at this one here. So equals this guy. And then over here, the probability of F given E is the second one. The accident was caused by a signal given that the accident. So for this one here, we're just going to grab this one. All right, and then here's the check. In order for you to have independence, the probability of E given F has to equal the probability of E. That is not the case, 21% versus 14%. So that's one check. These two are not very close. These are not very close. And if you check these two as well, they're not very close. So in all three cases, these two numbers are not equal. And if that's the case, then when we say that the two events are not independent. And if we want to know if two events are mutually exclusive, all we have to do is to look at the probability of E and F. If the probability of E and F is 0, then the two events are indeed mutually exclusive. In this case, the probability of E and F is not equal to 0. And the way we would interpret that in the context of train accidents with those two variables, the cause of the accident and the railroad company itself, we would say that if we knew that CSX was the railroad company that caused the accident, we wouldn't have any more or less information about whether it was a signal or communications accident. And if we knew that the accident was a signal and communications malfunction, we couldn't say that, oh, then it's more likely to be Union Pacific or it's less likely to be CSX. That's what not being independent means. Okay, so this is kind of a standard problem, and yours is going to be like this, but a little bit different. And then finally, the lottery problem. This is one where you get to enter in the price of the ticket. Let's say it's $7. Notice when I type in $7 here is the ticket price. The first prize amount comes $7. We want to give the lowest prize we want to give is the one that matches the cost of the ticket. Now, if this is going to be 7, then these numbers have to go up by a little bit. So maybe 8, because you want to have different prize amounts here for your lottery ticket. So maybe up to 10 and then up to, and then 15 and then maybe 20, and we'll go from there. There are several parameters about your ticket, and all of the parameters are down here. Your ticket has to match all of these items. So the cost to purchase your ticket must be a whole dollar amount. I selected 7 up here. The expected loss to the consumer should be less than $1. Now down here, you can see that every time a consumer buys that $7 ticket, they're going to lose over $5 of that. You want this number to be less than $1. Consumers are generally willing to lose $1 as they play this game, but they're not willing to lose $5 every time to play it. So to encourage consumers to continue to come back and play this game and use their winnings to buy new tickets and so on, we have to make it cheap for them to play. Another parameter here is that the grand prize must be $500,000. So everybody's going to have $500,000 in this spot. You can give one of those out, you can give 2 of them, you can give as many as you like. But you have to be careful because you have to meet all the other parameters of the ticket. There must be 8.4 million tickets sold, so everybody's going to have 8.4 million. I've designed this spreadsheet so that if you only change the green numbers, so for example, if you change this one to 3 million, then it automatically updates the losing tickets so that these numbers still add up to the 8.4 million. Another thing that you need is for the state to make a profit of more than 7 million. So this number here, which is the profit that they earn, is got to be more than 7 million. That's why these lottery tickets are created, to raise money for the state to pay off the state's bills. Sometimes they say they go to education, and sometimes they say they go to other things. And finally, you want to make sure that the probability of winning is greater than 0.25. And this is another thing that will bring back the consumers in playing this more often. If they're going to win 1 in 4 times, they're more likely to play than if they're going to win 1 in 30 times. So you want the probability of winning to be larger than 0.25. My ticket here matches that. My ticket here does have a ticket that makes a profit more than $7 million. I do have the 8.4 million tickets, and I do have the $500,000 grand prize. I also have a ticket that's legal, $7. However, this number down here is too big. So we need to change something about our ticket so that it brings this number down to a number between 0 and -1. And that would mean that the consumer would lose less than $1 on the purchase of this ticket. Here's your expected value table. So the way we get -7 here is that if the consumer buys the ticket for $7, that's cash out of $7. That's a -7. And then if they get a loser, then that's cash in of 0. So they end up losing $7. Down here, if they pay $7 and then win a $20 ticket, well, their net winnings would be 13. If you change the price of the ticket up to $12, then the first prize amount will be 12. And if you paid $12 for the ticket and you win $12, then your expected winnings would be 0. So that's how you get all of these numbers. You just take the ticket price, the prize amount, and subtract the ticket price. Over here, the number of tickets. So if you wanted to calculate the probability of winning, you just take the number of tickets of that prize amount. So the loser, there are 5.3 million of those. And if you take 5.3 million and you divide by the total tickets, 8.4 million, you have a 63.3 chance of losing this game. And you would calculate all the other probabilities in the same way. So for example, the probability that corresponds to 50,000, you just take the 50,000 and divide by the 8.4 million, and you get this probability of winning that prize. For the expected value calculation, you multiply these two numbers together to get this number, you multiply these two numbers together to get this number, and so on, all the way down the table. And then in the end, you're going to add up all those numbers, and that's going to be the expected value. Okay, so now everything is done. So as long as you just change the ticket price and then these green numbers in here, everything should update, and you can just take a look at them. All right, so starting back at 7, you can see that our profit is good enough. Our probability of winning is good enough. We have the right number of tickets. We have the right grand prize amount. We have a valid ticket amount, but our expected value is not in the range we want it to be in. So we can give away more money because our profit only has to be 7 million. So you might want to raise all of these numbers here so that you're giving away more money. You could probably even triple these. So maybe I'll change this one to, say, 200,000 tickets of that type, and then maybe 50,000 of this type, and maybe 10,000 of this type, and 5,000 of this type, and just kind of see where we go from there. Well, it didn't change much. Brought down this a little bit, but not a whole lot. So maybe I'll give away, let's see, could I afford to give away another 18 million here? Well, I suppose I could. So let's bump this up to maybe 1 million. All right, now we're up to 10 million. Still good, still good. That lowered this one. So maybe I'll go up to 200,000 on this one. But anyways, you just keep experimenting and experimenting and experimenting until all the numbers are correct. You can try my approach. You can also change the values of the ticket. So maybe if you wanted to increase this one to, say, $500 instead of $50, well, then you've given away a lot more money. And every time you update up one of these or up one of these, then that changes these numbers down here, and that's going to change the expected value. But we still have a way to go. If we wanted to give away another, if we give away another 3 of these, you can see that jacks up the winning amounts quite dramatically. You can see the numbers that change the expected value a lot and those that don't change it a lot. So you just basically trial and error until you find something that matches all of our criteria down here. All right, and when you're done, just go ahead and copy this. You can just maybe just do a copy like this and then paste it into your Word document, and then eventually create a PDF.